Hello, everybody. My name is Erli Wang from University of Queensland in Australia. Today I will present our work on POMDP solver. The focus of this work is to improve the capability of solving POMDP with large discrete action space. This work is jointly with my supervisors, Hanna, Kurniawati, and Dirk. Sequential decision-making is widespread in many domains. For example, space exploration, nurse-boarded in nursing facility, and airplane collision awareness in the mid-air. The key question to solve those problems actually is the same. That is, what actions should I take in order to maximize the long-term outcome, despite the various types of uncertainties. The partially observable marked decision process, POMDP, is a principled model for such decision-making under uncertainty. A POMDP can be described as follows. At each step, an agent is in some hidden state, takes action, it will move to the next state according to a transition function. And the next state will be partially perceived by some operating function. After each step, the agent will receive an immediate reward, and we repeat the process. The objective of POMDP is derived from the real function. Due to the uncertainty in the effect of performing actions and instancing, the agent never knows its exact location. Instead, we maintain an estimate of its current state in the form of belief. Even though POMDP is a nice mathematical framework for such robust decision-making, but has been considered impractical and is often abandoned for decades. Unfortunately, the past decade has seen a significant advances in approximate POMDP solvers. Nowadays, people can find good decision strategies for those types of POMDP problems. However, despite this development, finding good decision strategies for large discrete action space remains difficult. Most solvers today can only handle dozens of actions, but being able to handle much larger action space is crucial for dealing with more widespread applications. For example, in spoken dialogue system, the moderate size of a real system require at least 10 billion for actions, which means current solver are hard to be applied there. In fact, in POMDP, finding out the best policy matters how we compute the expected total return or Q value, as well as how we optimize the Q value over the action space. But the difficulty here is calculating the expectation here is computationally expensive because it cannot be computed in a closed form. Furthermore, if we want to find the best action to maximize the Q value, it will be more difficult. So to this reason, most solvers resort to enumerating all possible actions. But the issues comes up when the action space is large. So as a result, the planning horizons that the solver can look ahead will be significantly reduced and hence reduce the quality of a solution. To alleviate solving the POMDP with large discrete action space, recently there are several papers for those two aspects. If we can put restricted conditions on POMDP model, then linearized solver can be used here to reduce the computation complexity. And for the action selection, several papers have been proposed to deal with the continuous action space, which I think sometimes it will be easier to solve due to the continuity properties. In this work, the new algorithm we propose is called Quantile-Based Selector. In our QBASE, we will relax the continuity requirement and adopt the Quantile-based approach to find the best action. QBASE is an online solver. Similar to other kind of the online solvers, will adopt tree structure as our policy representation. By following those steps, the figure here shows a sample result of simulating the belief tree for multiple times. In QBASE, we try to avoid sweeping the whole action space whenever a new belief node is added to a search tree, because in the previous slide we have already identified this sweeping strategy may be not that efficient for dealing with a large action space. Conceptually, QBASE alleviates solving POMDP with large discrete action space by interleaving sampling actions with belief sampling. And we represent the uncertainty of selecting the best action by using the probability vector and use this information to sample actions. And to be more specific, it contains two-stage sampling. For the first stage, we try to construct a small subset which aims to reduce the action set. The set consists of two parts, the exploration and the exploitation. For the exploitation, it is determined by the actions entering the top row quantile of the current estimate of Q value. And for the exploration, it's just simply a sample of few actions uniformly at random from the entire action space without considering the first part. And the second stage is we apply the modified version of the cross-entropy method to solve the probability for those validity actions. And the first term quantifies how much the QBASE will trust the current estimate, and second part just following the standard proportional cross-entropy method. Once we got those two information, we will interleave those two stage sampling with a predictive tree to do the estimation. The two systems runs iteratively in batch mode. As a result, this will allow more computational resources to be allocated to the current permission actions, as well as it ensures that all the actions will be eventually validated. So in this slide, I will show you how QBASE adopts the two-stage sampling to guide the tree search. At the beginning, the search tree is nothing more than a belief node. We initialize the subset and the probability function for those two actions. And to ensure that current subset is being evaluated sufficiently, it will be only updated in a batch mode. Otherwise, we just draw an action from the current subset and to do the estimation. So we sample, keep sampling until some node in the search tree meets the batch conditions, and then we are going to do the two-stage update, and we will update the subset by the two-part exploration and the exploitation, and then we'll update the probability in a cross-entropy fashion. And once we have this update information, we will continue sample the tree until the maximum planning time is reached. So this is the idea of the QBASE. And how about result? We compare our QBASE with POMDP, which is considered one of the state-of-the-art solver in this community. And for example, we test is example. The goal of agent in the example is try to sample as many good rogues as many as possible and as soon as possible. So in this case, the size of action space increases as we add more number of rogues. So for this example, we test 3 different settings and leading the action space ranging from 13 to roughly 100. So for the comparison, we find that the performance of QBASE and POMDP are comparable with a given planning time. And those two figures show a median size and larger size for log sample with different planning type. So generally speaking, when the planning time is small, and both POMDP and QBASE perform equally poor. But if we give more planning time, so to here and here, the QBASE is able to generate better results than POMDP. Next example we test is navigation. In this example, the agent must navigate to the goal region to mark as red here, but at the beginning it can be only roughly known as several possible cells around here. And for the observation, when the agent meets the wall, it can feel the existence and the shape of surrounding worms. So note that even this kind of local observation is perfect, but it's not sufficient to make the agent state to be fully observable, because multiple states in this environment can yield the same observation. So the action space in this problem increase as we increase the dimensionality. In the paper, we tried the 2D up to 4D, leading the largest action space to roughly 2,400. And the general pattern we found the comparison here is as we make the problem larger and larger, the performance gap between QBASE and POMDP increase. That's good. Finally, we extend the attack problem to be multi-agent to catch the multi-agent to catch a multi-target. At the beginning, all the agents start at central, but the location of the target is unknown to the agent. So we represent as the uniform over the free space here. For the observation, each agent can detect the regions nearby, but even though the result of detection is perfect, but the agent cannot distinguish which target is being detected, nor exactly of the location in those surrounding cells. The goal of this problem is that all the agents try to collaborate with each other to catch all the targets as soon as possible and successfully. In the paper, we tried, so in the problem, the action size increases as we add more number of agents. So here we tried from the 2 agents up to 4 agents, leading the action space to up to the 10,000. And the general pattern from the comparison here is similar to what we saw in the navigation. That is, as the problem becomes more complex, the QBASE is able to generate substantial better result than POMDP. So here I want to show you animation for the 3 agents to catch the 3 target. As I said, at the beginning, all the agents start at central, and due to the location of the target is unknown, so we put uniform as background. So, but for the convenience of visualization, we put the hidden true target in array. So you will find that the background color, the background belief is changing over time because the agent is purposely moving away from the closed list agent. And you will also find that the probability at each corner is accumulating because the agent, the target will get stuck in this kind of the location. So this will be useful for the agent to catch the target. So here we will finish the task. So during this simulation, we find several interesting behaviors. For example, here the robot C, since there's the agent since there's a target nearby, but it cannot tell where the target is in this one, is this cell, or this cell. And the C tries to confirm the location by itself, but you will find that the C actually loses the detection of a target. And due to hunting in the centralized planning, and the robot A and B come back immediately to help C, and with the help of other agent now, the agent C is confirmed that the target and itself is in the same cell, which means it will be safe for A to catch the target. And up to now, so all this agent is around this region. So the best thing we can do is totally eliminate the possibilities of the agent in this cells. So you will find that robot B and C will check those corners simultaneously, and the black arrow shows the motion of the trajectory. And after that, in order to catch the risk target efficiently, so the ABC will choose a different corner to further check the risk. So the problem finishes until all the target is being successfully tagged. After the submission of ICAPS, we further scale up in action space. So here we put the action space to the 100,000, and the comparison is very clear. But it will be interesting to find that QBASE seems to find the good decision strategies fast. And additionally, if we give more planning time, the improvement of QBASE is much better than the POMDP. And the digit here I put here means the successful rate of completing the task. Okay, so if you forget about my task, and I will highlight everything in short sentences. In this work, we propose a new action selector called the Quantile. It uses quantile statistics to adaptively construct different parts of action space. And from our comparison, we found that QBASE is able to outperform the POMDP, which is state of art, when the POMDP with a large discrete action space. Okay, thank you for attention.
Where's the
Nice catch.
Good throw. Can you talk about the computational cost of sampling the actions?
Pardon?
The computational cost of sampling the actions.
You mean which case? QBASE?
Yeah.
Yeah. No.
You can't.
No. You mean sorry?
I mean, you scale to 100,000 actions. So how long does it take you?
Oh, okay. So first one, because this is online software, so we will just do the comparison with for example, the computational the planning time for per step is 1 second, and this one is 10 seconds for the per step. And after planning, it will execute the action, and it will reach to the next belief, and it will have another planning type, another planning budget to.
So it's 10 seconds for each information state.
For each step.
Yeah.
Yeah. Because this is online software.
Yeah.
Okay, short question.
Thanks for the talk. I was wondering if you tried your algorithm on settings like where the targets are moving and trying to escape, like you push it away their kind of situations. Have you tried your algorithm, or do you have any guesses how would it perform in those kind of settings?
So you're asking applying this algorithm to other domains?
Yeah, here like this, the targets were staying put, right? Like the red cubes. Like what if they are trying to escape?
So
Or
you
like-
mean this example? You mean the
It's even easier. Why is that?
So here the target is not fixed. So it will move. It will move. Actually, it will escape from the close list agent to the cells far away from the cover state.
Also, they are still performing in algorithm as well. So the targets are not.
So you will see this one. The target just will go away. So here, you will see, and this one.
That's the best thing that they
Yeah.
can do. Thank you.
Okay, thank you very much.